Hello, and thank you for watching. This presentation introduces SAND, a semantic-aware framework for industrial anomaly detection with noisy training data. In real manufacturing pipelines, the nominal training set is not always clean. It may contain subtle unlabeled defects, background outliers, or acquisition noise. These contaminated samples can weaken anomaly detectors that assume all training images are normal. SAND addresses this problem by using semantic region provenance during training. The key design is training heavy but inference light. Semantic priors guide learning, but the final detector does not require semantic segmentation or memory bank retrieval at test time. The motivation starts from a limitation of global memory matching. Memory bank methods store normal patch features and compare each query patch with its nearest neighbors. This is effective when the training data are clean. However, under noisy normal training, the global memory bank mixes features from different semantic regions. This creates two failure modes. The first is cross-region mimicry. A defect in one component may retrieve a normal-looking pattern from another component. This suppresses the anomaly score and may cause misdetection. The second is boundary artifacts. Patches near object boundaries may mix foreground, background, or adjacent parts. These mixed patches can behave like outliers and cause false alarms. SAND treats both cases as a loss of semantic provenance. The paper supports this diagnosis with a nearest neighbor analysis. For each patch, we compare two distances. The first distance is computed against the global memory bank. The second distance is computed against the memory subset from the same semantic region. Because the in-region subset is part of the global bank, the global distance is always no larger than the in-region distance. When this gap becomes large, the patch may be using an outside region shortcut. This indicates semantic mismatch and nearest neighbor retrieval. The right panel further groups this mismatch by patch purity. Low purity patches, which often appear near boundaries, show heavier mismatch tails. This confirms that boundary patches have less stable neighbor relations. These observations motivate to requirements: retrieve within the same region when reliable, and treat low purity boundary patches more conservatively. SAND first obtains coarse semantic priors before training. For each category, region-level keywords are generated as compact text prompts. CLIP aligns image features with these prompts for coarse text-guided localization, and SAM refines the masks into patch-aligned semantic regions. The resulting masks are projected to the patch grid. Each patch receives 3 cues: a region ID, a foreground confidence, and a purity value. These cues are not used as perfect segmentation labels. They only provide coarse region provenance. This distinction is important. SAND does not require pixel-accurate semantic masks. It only needs enough regional structure to make training signals more reliable. At inference time, all these semantic priors are removed. The full SAND pipeline can be summarized by 3 training time signals. First, RAM/B changes where a patch is compared. If a patch has reliable region evidence, its nearest neighbor distance is computed from the corresponding in-region memory subset. If the region queue is uncertain, or the corresponding region bank is too small, SAND falls back to the global memory bank. This fallback is important. It prevents imperfect region partitions from becoming a new source of training noise. Second, SWAT changes how much we trust each pseudo-label. The reliability weight is computed from foreground confidence and region purity. A high-purity foreground patch receives a stronger weight. A boundary or background patch receives a lower weight. The same reliability signal also raises the pseudo-label threshold for uncertain patches. In other words, unreliable patches need stronger distance evidence before they are treated as anomalies, and they contribute less to the loss. Third, RCRR changes what structure is distilled into the detector. During training, region queues encourage features from the same region to be compact, while different region prototypes are separated. A normal-only gate reduces the risk of pulling true anomalies back into normal prototypes. This is why SAND can use semantic priors during training, but remove them during inference. The detector absorbs region-consistent structure during training, without requiring semantic priors or memory retrieval at test time. After introducing the training design, we now look at how it behaves under noisy normal contamination. The main results compare detection and localization on MV-TEC-AD and Visa as the noise ratio increases. A clear pattern can be observed. Patch core is still competitive when the training set is clean, but becomes less robust once contaminated samples are included. Dynomaly also performs well at image-level detection in the clean setting, but its localization degrades more clearly as noise increases. Noise-aware baselines such as SoftPatch, SoftPatch Plus, and InReach reduce this degradation, but SAND remains more stable in the mid to high noise regime. At 10% noise, the C-squared head reaches 99.2 and 98.6 on MV-TEC-AD. On Visa, it reaches 95.1 and 99.1, exceeding the strongest baseline by 1 point for points for image level detection and 0.8 points for localization. The robustness curves provide the same comparison from another protocol. Here, the training contamination may overlap with the test split, which makes the setting more sensitive to noisy memory construction. As the noise ratio increases, several competing methods degrade more noticeably. PatchCore shows a steep drop, and SoftPatch Plus gives weaker localization than in the no-overlap setting. In contrast, SAND is less sensitive to whether the contamination overlaps. It remains strong for both image-level detection and pixel-level localization. This suggests that the improvement is not tied to a specific protocol, but comes from more reliable learning under contaminated training data. The next point is deployment efficiency. Some strong baselines still rely on large models or test-time memory matching. For example, Dynomaly can be competitive under low contamination, but it uses a much larger model. Retrieval-based methods such as SoftPatch, SoftPatch Plus, and InReach are also limited by nearest neighbor matching during inference. SAND avoids this test time cost. Semantic priors and memory retrieval are used only during training. At inference, the model uses a frozen feature extractor and a lightweight detector. The C-squared head version is 42.7 megabytes and runs at 44.1 frames per second on an RTX 4090. The FFN version reaches 52.5 frames per second. This shows that the robustness improvement is compatible with practical deployment constraints. The qualitative results provide a visual check of the localization behavior. Each example shows the input image, the ground truth anomaly mask, and the predicted SAND heat map. The examples are selected from both MVTech-AD and Visa, so they cover different object structures and background conditions. The heat maps are not intended to show perfect segmentation. The important observation is that the high response regions are generally aligned with real defect areas. This supports the pixel-level results and shows that SAND preserves useful localization ability under noisy training. The examples also help connect the method with the motivation. By reducing cross-region confusion and boundary-induced noise, the detector produces more coherent anomaly maps. The background perturbation study further tests robustness beyond clean benchmark settings. Many standard anomaly benchmarks are collected under controlled backgrounds. In real production lines, however, backgrounds may include textures, repeated patterns, reflections, and illumination changes. These variations can introduce background-driven false matches, especially when the training data are already contaminated. Here, backgrounds are replaced under 10% noisy normal contamination. SAND obtains the highest average on MVTech object classes with the C-squared head. On Visa, all methods suffer from background perturbation, but SAND shows a smaller performance drop than Dynomaly and SoftPatch Plus. This suggests that region-aware retrieval and purity-aware weighting help stabilize detection when background evidence becomes less reliable. The ablation results explain how the three training time components contribute. Starting from the global memory baseline, RAM gives cleaner retrieval evidence by using region provenance. It improves image-level detection on Visa, but the localization gain is still limited. This means that region routing alone does not fully solve boundary ambiguity. When SWAT is added, the localization improvement becomes clearer. This matches its purpose. Purity-aware weights and adaptive thresholds stabilize pseudo-supervision for boundary mixed or low-confidence patches. RCRR further complements the other modules by distilling region-consistent structure into the lightweight detector. The full model achieves the best results on both datasets. The sensitivity results also show that reasonable choices of purity threshold and region bank size keep performance stable, so the method is not overly dependent on a fragile hyperparameter setting. To conclude, SAND addresses noisy industrial anomaly detection by preserving semantic provenance during training. It identifies two failure modes of global memory matching, cross-region mimicry and boundary artifacts. It then introduces three training time mechanisms: region-aware retrieval, reliability-aware pseudo-supervision, and region-consistent representation regularization. The experimental evidence includes main benchmark results, robustness curves, background perturbation studies, qualitative localization, and ablations. The final detector remains lightweight because it does not require semantic priors or memory retrieval at inference. The overall message is simple: use semantics to guide training, then keep inference compact and standard. Thank you for watching.